I don't have a homework assignment made up yet for 4.3, but I'll get one made up and released in WebAssign, and it'll be due Monday night. Okay. So our quiz on Monday, I guess, will be just over sections 4.1 and 4.2. All right. So in the graph of a function, f prime of x, right, tells us the slope or the steepness of the curve, right, at each value of x. Tells us where the graph of the function is increasing, where it's decreasing. And the second derivative, which we're going to talk about now, tells us about the concavity of the graph, okay, at each value of x. And so with those two, right, derivatives and some other stuff, right, we can get a pretty good graph. So top page, it's hard to handle. So top page 1, okay, it defines what we mean by concavity, concave upward, concave downward. So if the graph of f lies above all of its tangents on an interval, right, this interval are values of x, okay, then it is called concave upward on I. Okay, so down here, we have part of the graph of a function, okay, and you can see that from this point right here to the right, the graph of the function is above all the tangent lines on that part of the curve. Right? So here we got 1, 2, 3 different tangent lines, and the graph of the curve, okay, is above all 3 of those tangent lines. So when that happens, that part of the curve is said to be concave up. Okay. If the graph of f lies below all of its tangent lines on an interval, okay, it is called concave downward. So you can see on this part of the curve, all the tangent lines are above the curve. Right? The curve is below the tangent lines. And so we say that part of the curve is concave down. Okay. Now, one way that I remember concave up from concave down, okay, apart from this formal definition, is if you think of this part of the curve here as a cup, the cup will hold water. And if the cup holds water, the graph is concave up. In this part of the graph, the cup is upside down. It won't hold water, and so we say it's concave down. Okay. That's how I remember distinction between concave up and concave down. If it holds water, it's concave up. If it doesn't hold water, it's concave down. Okay. So on the next page are the graphs of a function f of x, its derivative function f prime of x, and the second derivative function f double prime of x. Okay? And one of the conclusions that we're going to note, is that the second derivative is positive for those values of x where the graph is concave up, and the second derivative is negative for those values of x where the graph of f of x is concave down. So if you flip your page over, here's the graph of f of x at the top. Okay. And you can see that to the left of the y-axis, okay, the graph is concave down. Right, the cup doesn't hold water. And to the right of the y-axis, right, the graph is concave up. Right, the cup does hold water. Okay. In exam 2, right, I gave you a graph of a third-degree polynomial, and you had to graph the first derivative, right, function. And so, with the graph of this function f of x, right, you can see here at the top of the hill, the slope of the tangent line is 0. And here at the bottom of the hill, the slope of the tangent line is 0. okay? And to the left of x equals minus 2, right, the graph is increasing, the slope is positive. And to the right of x equals minus 2, and to the left of x equals plus 2, the graph is decreasing, and the slope is negative. And then to the right of x equals 2, graph is increasing, right? The slope is positive. And so that's reflected in the graph of its derivative function down below. Okay. Starts off, graph of the derivative function, right? Starts off positive, and it goes down to 0 at x equals minus 2, right? Because that's where the tangent line is equal to 0, right? So the tangent line is 0 at x equals minus 2. And then the slope is negative from x equals minus 2 to plus 2, right? So the graph of f prime of x is below the x-axis. This is the x-axis. And then for x greater than 2, the slope is positive again, and you can see the graph of f prime of x is above the x-axis. Well, the graph of f prime of x is the graph of a function. And so if we differentiated that function, right, we would get the graph of its derivative. And so down below is, it's almost too big. Down below is the graph of f double prime of x, right? The second derivative of f of x is the graph of f of x, but the graph of second f double prime of x is also the derivative function of f prime of x. So f double prime of x, right, gives the slope of the graph of f prime of x, okay? Because it's the derivative of f prime of x. So the first derivative of any function, right, gives you the slope. So you can see that the slope of f prime of x is negative for x less than 0, right? Slope is negative, right? I'm not saying f prime of x is negative. I'm saying the slope of the function f prime of x is negative for x less than 0. And that's reflected in the graph of f double prime of x. The value of the second derivative is less than 0 for x less than 0. Right? Second derivative takes on negative values for x less than 0 because the slope of the curve of f prime of x is negative for x less than 0. So up above, you can see that f prime of x is a decreasing function for x less than 0, and the slope of f prime of x is negative, right? It's a decreasing function for x less than 0, and the slope of the curve of f prime of x is negative. Okay? And that's reflected in the graph of the second derivative, right? Its values are negative for x less than 0. Okay? Conversely, f prime of x is increasing for x greater than 0. You can see that, right? For x, from x equals 0, for x greater than 0, right? F prime of x is an increasing function, and the slope of the graph of f prime of x for x greater than 0 is positive. And that's reflected in the graph of the second derivative, right? Because the graph of the second derivative gives you the slope of the graph of the first derivative. And so since the graph of the first derivative is increasing for x greater than 0, right, means it has positive slope, the values of the second derivative are positive for x greater than 0. So now, if you look at, compare the graph of f of x at the top with the graph of the second derivative at the bottom, you can see for the value for x less than 0, where the graph of f of x is concave down, the values of the second derivative are negative. And for the graph of f of x for x greater than 0, where the graph is concave up, okay, the values of the second derivative are positive. So there's a connection between the sign of the second derivative and whether the graph of f of x is concave up or concave down. Okay. Any questions on that? Okay. So if you flip the paper over, we have what's called the concavity test. And it says, it summarizes what we see on the previous page. If the second derivative is positive, greater than 0, for all x in an interval I, then the graph of f is concave upward on that interval. If the second derivative is negative for all the values of x in an interval, then the graph of f is concave, oh, jeez, downward. I have an error. That should be downward. It should be concave downward. It's amazing how I can miss these things proofreading in my office, and I get in here and all of a sudden they just stand out. Can't be both concave upward for positive and negative values of second derivative. Okay. So yeah, please scratch that out, word up, coordinate, and write down. Okay. So if the second derivative is negative for all x in the interval, then the graph of f is concave downward. Okay. All right. Next, we're going to talk about what's called an inflection point. So we're using the same curve from page 1, okay, where it's concave downward up to this point, and then it's concave upward after that point. That point where it switches from being concave downward to concave upward is called an inflection point. And I guess POI stands for point of inflection. Okay? So a point P on a curve is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward, or from concave downward to concave upward. So in the examples that follow, we're going to use the same functions as yesterday, and we're going to find the intervals where the graph of the function is concave upward and where it is concave downward, and where the point of inflection is. So in the first example, we have the third degree polynomial f of x is equal to x cubed minus 3x squared minus 24x plus 92. And you know, yesterday we did the first derivative test to see where the graph of this function is increasing, decreasing, right, where the local maximum was, where the local minimum is. And so we have to do something similar in finding the intervals where the graph is concave up and concave down. Okay. We got to calculate the second derivative. And so, you know, to do that, first you got to calculate the first derivative. So f prime of x is equal to 3x squared minus 6x minus 24. And then you get second derivative, we differentiate the first derivative. And derivative of the first derivative is 6x minus 6. Then he set second derivative equal to 0. And solve for x. And when we do that, we get x is equal to 1. Now, the values of x that make the first derivative equal to 0, we had a special name for that. Remember what that special name is? Critical numbers, right? This is not a critical number, right? This is does not, the values of x make the second derivative equal to 0, do not have a special name. Okay? Critical numbers only apply to the first derivative. Okay? So then, we take these values of x that make the second derivative equal to 0 and use them to divide up the real number line. And then we have to do a test point method with the second derivative. So, test point, value second derivative. So 0 is less than 1. So when I put 0 in for x in the second derivative, we get minus 6. Second derivative is negative. So for all values of x less than 1, the second derivative will be negative. So is the graph concave up or concave down on that first interval? So we concave down because the second derivative is negative. And so graphically, how I indicate that it's concave down, I draw it here. Now for x greater than 1, I use 2 as my test point. And when I put 2 in for the second derivative, I got plus 6. So the graph of f of x for x greater than 1 is concave up now, right? Now, I'm not saying that the graph, excuse me. Right, I didn't give myself enough space. I'm not saying that the graph looks exactly like this, right? But I'm just using it to indicate it's concave down to the left of 1, concave up to the right of 1. Then at x equals 1, what's that point going to be called? Yeah, point of inflection or inflection point, right? So at the bottom of your page, we know what the x coordinate for the inflection point is. Now we got to calculate its y coordinate. And f of 1 is, when I did the arithmetic, I got f of 1 is equal to 66. So the inflection point, okay, is at 166. Okay? Now sometimes, right, when we're doing this, we don't necessarily want to know the point, right? We just might want to know that there's an inflection point at x equals 1. So sometimes you'll do problems where they just want to know at what x coordinate, at what value of x is the inflection point. Okay? Where is the graph concave up? From 1, right, to values of x greater than 1. And where is it concave down? For values of x less than 1.
this at the point of inflection?
That is an excellent question. And there is a tangent line. But here's the deal. If I have a good colored chart. You know that all the tangent lines where this graph is concave down, right, are above the curve, right? From a definition on page 1. And for where the graph is concave up, all the tangent lines are below the curve, right?
Yes.
There's a point of tangency, right? But to the left of this, the tangent line is above the curve, and to the right of that point, the point of tangency is below the curve. Yeah. So, but it only touches the curve at that one point, or goes through the curve at that one point. Okay. So it's got to be above the curve, right, to the left of the point of tangency in this case, and it has to be below the curve to the right of the point of tangency. Okay. In order, right, from our definitions. Okay. That's a good question. Okay. All right. Any questions on this example? Nada? Okay. So this is all that, remember, all these problems, right, we did yesterday. In finding the local maximums, the local minimums, where it's increasing, where it's decreasing. So in not the next section, the section after that, right, we're going to pull together everything we've done this semester with graphing, right, and graph various functions. All right, so in this next example, f of x is equal to the cube root of x, which you know is x to the 1/3 power. And we got to find out where the graph is concave up and where it's concave down. Okay. So we need the second derivative. So the first derivative is 1/3 times x to the minus 2/3. And then when we differentiate the first derivative, 1/3 times minus 2/3 is minus 2/9. And then when I subtract 1 from minus 2/3, I get minus 5/3. Or minus sign in the exponent means reciprocal. So this can be written as minus 2 over 9 times x to the plus 5/3 power. Well, there's no value of x that makes the second derivative equal to 0, but there is a value of x that makes the second derivative undefined, or the second derivative doesn't exist. And I guess we should already know that, because from yesterday's work, the first derivative doesn't exist at x equals 0, so the second derivative can't exist. Okay. So even where the second derivative doesn't exist, you can still have a point of inflection. Okay. All right. So you got to do the test point method again on the second derivative. And so for x less than 0, right, you use -1. The second derivative evaluated at -1. -1 to the 5/3 power is going to equal what? By venture a guess.
Rearrange the -1.
-1 to the 5th power is equal, and then the cube root of -1 is, yeah, so -1 to the 5/3 power is just -1. So this is so then we have -2 over 9 times -1, which is plus 2 9. Okay. So, second derivative is positive, concave up or concave down? Concave up, right? Now, again, I'm not saying the graph looks like this. I'm just drawing this cup to indicate it's concave up, because we're going to find out the graph does not actually look like that. Okay. And we actually graphed it on the board yesterday. To the right of x equals 0, right, you can use +1 as your test point, and the second derivative evaluated at x equals 1 is equal to -2 9 negative. So the graph is concave down to the right of x equals 0. Okay. So by our definition, point of inflection, do we have an inflection point at x equals 0? Does the concavity go from upward to downward? So even though the second derivative doesn't exist at x equals 0, there's a point of inflection, right? Remember, the only condition on the point of inflection, if f is continuous there, right? And the graph of f of x is continuous at x equals 0, even though the first derivative doesn't exist. Okay? And what we learned yesterday was at x equals 0, the tangent line is vertical. And vertical lines, right, have an undefined slope. Okay?
Is the point of inflection where f prime of x equals 0 or is undefined?
No,
Or
it
it's
has nothing to do with that.
Okay.
Yeah, f prime of x has nothing to do with the point of inflection.
I'm sorry, I meant f double prime.
Yeah, so f double, so the second derivative is either equal to 0 or undefined.
And so that point then becomes the point of inflection, or not always?
Not always.
Not always, okay.
It becomes a point of inflection because we went from concave up to concave down
Okay.
at x equals 0.
So there will be times where it won't do that.
Yeah. Okay. All right. Are we cool? Everybody got that? All of that?
Does the point of inflection also count when it goes from negative to positive? It just means
Yeah.
it's a change, right?
Yeah.
Okay.
Yeah, yep, that's exactly right. Point of inflection just means there's a change in concavity, okay, from left to right. It's called an inflection point if f is continuous and the curve changes from concave upward to concave downward, which is what we have here, okay. In the previous example, we went from concave downward to concave upward, okay. So the concavity at the point of inflection just has to change from up to down or down to up, okay. Would be an inflection. All right. So where are we at? So to get the inflection point, they evaluate f of x at x equals 0, and cube root of 0 is 0. So the inflection point is the point 0, 0, right? It's at the origin. Where it's concave up, from minus infinity to 0, right? Or for x less than 0. And it's concave down for x greater than 0. All right. So let me give you a visual. We graphed this yesterday. Graph it again. But the graph of the cubing function, remember it has a vertical tangent line going through the origin. Looks something like this. Okay. This is the graph of f of x equals the cube root of x. Okay. And so, to the right of the y-axis, right, you can see it's concave down. All the tangent lines are above the curve. And to the left of the origin, okay, graph is concave up. All the tangent lines are below the curve. Okay. Now it's hard to, you can't, using the cup analogy, right? Neither the to the right of the y-axis or the left y-axis looks like a cup, but that's why I sort of use that analogy. Okay, that analogy defining concave up, concave down with a bit of a grain of salt. Okay. But that's what the graph looks like. All the tangent lines on the graph to the right of the origin are above the graph, and all the tangent lines are below the graph to the left of the origin. Okay? So it's concave down to the right of the origin and concave up to the left. And the origin is a point of inflection because it goes from concave up to concave down at the origin. All right, any questions on that one? All right, so you flip over your paper, your handout. We got one more. We have f of x is equal to x cubed plus 12x squared plus 5. Where is this graph concave up, concave down? You need the first derivative. And then you need the second derivative. Then we set the second derivative equal to 0. Solve for x. And we get x is equal to minus 4. So if this graph of this function has an inflection point, it's going to occur at x equals minus 4. Okay. Here's minus 4 on the real number line. All right. So for values of x less than -4, you can use -5 as a test point. And the second derivative evaluated at -5, -30 plus 24, which is -6. It's negative. Concave up or concave down? To the right of -4, you can use 0. The second derivative evaluated x equals 0 is plus 24. Up or down? Up. You guys are getting the hang of this. Do we have an inflection point at x equals -4? Does it go from concave down, concave up? We have an inflection point. So, the inflection point, we need to know what f of -4 is. That doesn't sound like a lot of fun to evaluate. -4 cubed plus 12 times -4 squared plus 5 is equal to -64 plus 48, 96, 192. -4 squared is 16. 16 times 10 is 160. 2 times 16 is 32. 116 32 is 192. Which is equal to 128, 133. Right? So our point of inflection point, is at -4, 133. Where it's concave up, is for x greater than -4. So what do we do? -4 to infinity. Concave down. Minus infinity. To -4. Any questions on it? Nada? Okay. All right. So you flip over your document, your handout. Now this is a neat little test. That we're going to talk about next. Okay. It's called the second derivative test. Okay. It's a very time-saving test when you're looking for local maximums and local minimums. If you can use this test. Okay. You don't have to do the test point method with the first derivative. Another application of the second derivative is the following test for identifying local maximum and minimum values. It is the consequence of the concavity test and serves as an alternative to the first derivative test. Okay. So the concavity test, right, top of page 3, which says if the second derivative is positive, then f is concave upward. If the second derivative is negative, then the graph of f is concave downward. So So it speeds things up in finding the local maximums and local minimums if you can use this test, okay? But you notice, right, the first derivative has to equal 0, so the first derivative has to exist, right, and equal 0. If it doesn't exist, you can't use this test. Okay? So we're going, from these two functions from yesterday, okay, we're going to find the local extreme, right, the local maximums and the local minimums. All right, so the first one is f of x is equal to x cubed minus 2x squared, oops, minus 3x squared, minus 24x plus 92. Okay. So first thing we got to do is find all the values of x that make the first derivative equal to 0. Okay. And we did do that yesterday. So f prime of x is equal to 3x squared minus 6x minus 24. And then you set the derivative equal to 0. And I remember factoring out a 3, or if you divide by 3, you get x squared minus 2x minus 8 is equal to 0. And we got x minus 4 times x plus 2 is equal to 0. And then our critical numbers were x equals 4 and x equals minus 2. You know, this is all in yesterday's handout. And those indeed are called critical numbers. Okay. Now the question is, if these values of x, okay, at x equals 4, do we have a local maximum or local minimum or not? Or neither? Same with x equals minus 2. Well, the second derivative test, right, says if the second derivative at x equals 4 is positive, then we have a local minimum at x equals 4. If the second derivative is negative, then we have a local maximum. Okay. So, the second derivative, which we calculated earlier today, is equal to 6x minus 6. So what's the second derivative at x equals 4? What's its value? 6 times 4 minus 6 is equal to 18. So we have, that's positive, okay? And since the second derivative is positive, we have a local minimum at x equals 4. Okay? And the reason for that, okay, and remember what the graph looked like. The graph looked like something like this. So here at x equals 4, the point, right, the slope of the tangent line is 0. And because the concavity is positive, right, the second derivative gives you the concavity. Since the concavity is positive, it has to open up or be concave up, and so it has to be a minimum. Okay. The only way you can have positive concavity with a slope of the tangent line 0 is if it opens up. Okay. At x equals minus 2, the second derivative is equal to, what, 6 times minus 2 minus 6, which is negative 18. So second derivative is negative, so we have a local maximum at x equals minus 2. So here at x equals minus 2, the slope of the tangent line is 0, right? That's what the first derivative told us. The slope of the tangent line is 0 at x equals minus 2. Concavity is negative, so it's gotta be concave downward. The only way you can have a 0 slope on the tangent line and have it be concave downward at that point is if it's a local maximum. Any questions on that? That's a lot faster than doing the first derivative test, right? Test one, where's it increasing, where's it decreasing, where's it increasing again? All right, so let's take a look at the next one, the last one. And we have, yes ma'am.
So if we were asked to find the y coordinates for the local maximum and minimum, and then we would just plug our 4 and our negative 2 back into
F of x.
it's just f of x.
Yeah, right. Because that'll give you the fx is the y coordinate
Right.
in the graph.
Okay, thanks.
All right. So lastly, we have, right, and then these 2 points, right, match. We didn't actually calculate the y coordinates, right, but the x coordinates, right, match the x coordinates from yesterday's first derivative test. Okay. All right. Lastly, we have f of x is equal to x cubed plus 12x squared plus 5. First, you got to get critical numbers to see where, if anywhere, the first derivative is equal to 0. And critical numbers are x equals 0 and x equals minus 8. Again, these should be in your notes from yesterday, right? Yesterday's handout. So determine whether there's a local max or min at 0, and at x equals minus 8, we need the second derivative. And second derivative is equal to 6x plus 24. So at x equals 0, determine if there's a local max or min, we gotta evaluate the second derivative at x equals 0. And 6 times 0 is plus 24 is equal to 24. Right? That's positive. So the graph is concave up at x equals 0, and so we have a local minimum. equals minus 8, the second derivative is equal to 6 times minus 8 plus 24, which is equal to minus 24. That's negative, so the graph is concave down. At x equals minus 8. So it's concave down. Slope of the tangent line is 0. So it's got to be a local maximum. And that should be in agreement with yesterday's conclusions, right? So we have a minimum at 0, 5, right? It's the y-intercept. And we have local maximum at minus 8. 260 was way up here. And so the graph went down. Right, so we have a local maximum at x equals minus 8. And we have a local minimum at x equals 0. And then there's a point of inflection in there. Okay. Where it goes from concave down to concave up. Okay. Any questions on this? So now you're going to have everything you need to successfully complete the 4.3 of sign home. Okay. Now I'll try to get that posted.